In this video, we're going to reapproach the problem from the first guided practice for weak acids, and we're going to look at acetic acid solution if we use the quadratic. 0.000671 versus 0.025 was about 2.5% of the starting amount, and we had made the assumption that we could just ignore subtracting that in our calculation. How good of an assumption was that? How would it affect our pH if we did account for that? So let's redo this with the quadratic. Well, I have a solution of 0.025 molar acetic acid. Some of it's going to dissociate. You're going to have less starting material at the end. You're going to make some product as a result. Whatever dissociates, you're going to make that much product. Since you started with no H plus and acetate, you're going to have X amount of them at the end. What is that going to give us if we don't simplify, though? Well, in this case, my Ka is still going to equal my products over my reactants. It's going to be my H plus, my AC minus, all over my HAC. So 1.8 times 10 to the minus 5 is going to equal X for my H plus, X for my base, and 0.025 minus X, we're going to keep that minus X in. Well, as a result, I've got to multiply it out a little bit. So multiply this part up. We're going to end up with 4.5 times 10 to the minus 7 minus 1.8 times 10 to the minus 5x. So 0.025 times 1.8 10 to the minus 5 gives us our 4.5 here. And x, well, negative x times 1.8 10 to the minus 5 gives us our minus 1.8 10 negative 5x. All that has to equal x squared. So we just multiply the bottom up to the other side of the equation. Rearrange to set equal to 0. 0 equals x squared plus 1.8 times 10 to the minus 5x as we move it over to the right side, and it's going to be minus 4.5 times 10 to the minus 7 as we subtract the constant over to the other side. We have this arrangement. Now we can do the quadratic. Negative b plus or minus square root b squared minus 4ac all over 2a. Our A is out here in the front. Here's our B. Here's our C. A is just 1. There's nothing in front of that X. Negative 1.8 times 10 to the minus 5 plus or minus the square root of 1.8 times 10 to the minus 5 squared minus 4 times 1 times negative 4.5 times 10 to the minus 7. All that divided by 2. The plus route, our x is going to be 6.62 times 10 to the minus 4, and then subtract route, our x is going to be negative 0.00068. Well, we can't have a negative value for our final concentrations of our products, so it must be the positive value from the addition. So this is the only real value that makes sense chemically. If we want to find our pH is going to be the negative log of 6.62 times 10 to the minus 4, which is 3.179. To compare to before, we'd found that our X previously was 0.000671 versus 0.000662. Our previous pH was 3.173 versus 3.179. They do make a slight difference when you account and don't simplify, but we only had 2 sig figs for our starting concentration, which means we really just get 2 sig figs in our answers. This would round slightly, 3.18 versus 3.17. So it can make a very tiny difference in some situations, whether you use the quadratic or you simplify, but as long as your ratio of concentration versus your Ka, put your concentration at about 400 times greater than your Ka value, the difference isn't enough that we're concerned about. Rounding error will usually introduce a bigger difference. And so we can simplify in most situations.